Today we're talking about capacitors, the electronic secret sauce. I call capacitors the secret sauce for two reasons. One, capacitors are involved in almost every interesting circuit. And two, they are secret because almost everything in electronics is a secret for almost everyone. Capacitors provide the sauce in a circuit. The frequency equalization, the timing, the unwanted signal elimination, the memory, the tone controls, onward and onward. Time and frequency. Before looking at some of the ways capacitors are used, a look at the two ways of measuring varying signals is important. Measurements of voltage against time are usually used for slow-moving signals and for signals which are random. In this video, the term volts per second will be used in discussing the rate of change of voltage with time. If the signal is regular, changing in a repetitive way, measurements use voltage against frequency. Frequency is usually measured in cycles per second, which is the number of repetitions of the signal in 1 second. 1 cycle per second is called 1 Hertz, after Heinrich Hertz, the first physicist to experiment with radio. It is possible to convert from one measurement style to another in several ways. The most common conversion schemes are the FFT and the inverse FFT. Beyond confusing you by saying that FFT stands for fast Fourier transform, there is no need to mention any of this again. Just remember volts per second, cycles per second, and maybe hertz. A capacitor is two conductive plates separated by an insulator. If a voltage is applied across the plates, electrons will pile onto one plate and leave the other. The two plates will have an electric attraction between them, holding the negative and positive charges in place. An unchanging voltage charges the capacitor up to the voltage and then stops. Current flows while the capacitor is charging. A changing voltage charges and discharges the capacitor, so that current flows almost as if the capacitor weren't there. In the time view, the faster the rate of change, the more volts per second, the more easily current flows through. In the frequency view, the higher the frequency, the more cycles per second, the more easily current flows through. Let's look at some numbers. In the case of a resistor, a circuit with 1 volt across a 1 ohm resistor will have 1 ampere flowing through it. For the capacitor in the time view, a circuit with 1 volt per second rate of change across a 1 farad capacitor will have 1 ampere flowing through it. The resistor, 1 volt, 1 ohm, 1 ampere. The capacitor, 1 volt per second, 1 farad, 1 ampere. Also consider these: 1 volt per second, 1,000 microfarads, 1 milliampere. And 1 volt per second, 1 microfarad, 1 microampere. The time view, with volts per second as the measure, is only occasionally used, even though it can often make a circuit easy to understand. In the frequency case, the capacitor acts as if it were a resistor where the number of ohms lowers as frequency rises. Here's the formula for the ohms, where frequency is in kilohertz, thousands of cycles per second, and capacitance is in microfarads, millionths of a farad. Resistance and reactance. In the resistor case, we talk of ohms of resistance. To distinguish the capacitor from the resistor, we talk of ohms of capacitive reactance. The capacitor voltage divider. The two-resistor voltage divider is the most important circuit using resistors. It is easy to understand that the voltage is divided by 2 if the two resistors are equal. The resistor-capacitor voltage divider is the most important circuit using a resistor and capacitor. When the resistance equals the capacitive reactance, the voltage is divided by the square root of 2, lowering about 30%. Low-pass and high-pass filters. There are two forms of resistor-capacitor voltage divider. The low-pass filter with the resistor on the input side, and the high-pass filter with the capacitor on the input side. In the low-pass filter, the reactance decreases with frequency, grounding more and more of the signal. In the high-pass filter, the reactance decreases with frequency, putting more and more of the signal across the resistor. Filter examples. There are thousands of different designs using the high-pass and low-pass filters. Here is a very common example, generally used in audio amplifiers. This circuit combines a resistive divider, a low-pass filter, and a high-pass filter. Here are some usable values. Using a big resistor in parallel with the capacitor and a small resistor in series with the capacitor ensures that all the filters and divider act independently. This makes the analysis easy. The low-pass filter passes everything under 20 Hz. The high-pass filter passes everything over 20,000 Hz. The resistor divider divides the voltage between 20 and 20,000 Hz by 100. By combining high-pass and low-pass filters like this, almost any frequency response can be produced. Here is one more example. The classic James Boxendall tone control circuit. The bass control is a low-pass bass boost and high-pass bass cut filter. The treble control is a high-pass treble boost and low-pass treble cut filter. When each control is in the center, the high-pass filters cancel the low-pass filters, giving flat response. A couple more notes for those actually wanting to build something. First, the ground plane. Every pair of wires or circuit traces forms a capacitor. If a circuit is misbehaving, it is usually an unwanted circuit through a capacitance between two conductors. To minimize the effect, most designers cover one side of a circuit board with a continuous sheet of metal connected to ground, called a ground plane. With a ground plane, a conductor's grounded capacitance is greater than any capacitance between conductors, grounding unwanted signals. Putting a ground plane on your circuit board is the easiest way to eliminate potential problems. The second point is the importance of what are called decoupling capacitors. These are fairly small capacitors placed around the board between the power and ground. Any unwanted effects on the power lines can be shorted to ground by these capacitors. Large electrolytic capacitors often don't do much at high frequencies, so the decoupling capacitors are small and close to the parts of the circuit to do what the large caps can't. A ground plane and decoupling capacitors are the two most important steps to ensure a circuit works as it should. If your circuit output should be this, and it is this, the decoupling capacitors and a ground plane are the best things to try. Thank you.